we are not sure that after time t equal to 0, whether or not this is a series RLC circuit or a parallel RLC circuit. Now this value S1 and S2, they are both the real values and they are distinct values, and therefore the response is overdamped, as I have explained. In S1 and S2 provides us information about the alpha and the damping frequency omega d. So these two values are used. Assalamu alaikum. I welcome you all to this short tutorial on the second order circuits. In the previous videos that I recorded, we discussed only about those second order circuits where it was quite obvious that the RLC elements are either connected in series or they come in parallel. However, there is not always the case when it is evident that the devices are connected in series or parallel. For example, this circuit has two inductors. Let me draw them. And we have two resistances. Let us say this is R1, this is R2, this is L1, and this is L2. It is quite obvious that there is no such way that we can have an equivalent resistance R, or we can get the L equivalent for these two inductors, because they are neither connected in series nor they are connected in parallel. Here we have the current flowing through this L2 is different than the current flowing through L1, and therefore one may say that they are in parallel, but when we see that this is connected between node A and B, while this inductor L2 is connected between node C and B, and therefore we can't say that the inductances L1 and L2 are connected in parallel. The similar sort of a case also arises when we have a capacitor network. For example, I have one capacitor C1 connected here, then in between C1 and C2 there is another resistance. There is a resistance which is R. In this particular case, we cannot determine whether the capacitors C1 and C2 are connected in parallel or not, or they're connected in series. And therefore, there must exist some generic method through which we can identify if a given circuit containing either two inductors or two capacitors or some other configuration, if they are a second order circuit or not. For this, we have a general procedure to find out the response of such circuits, and the steps for a general solution of second order circuit is as follows. So in the first step, for any energy storage element, if we want to take the transient analysis as well as the steady state analysis, the first step is to identify or calculate the initial conditions. These initial conditions could be the initial current through the inductor or the pre-stored value of the voltage in a capacitor, and therefore generically I can write it as this x0, and then the rate of change of that quantity with respect to time, and the final value, which is not the initial condition but a condition which we can say in a steady state condition. So it's better that if I may say or steady state condition, so that we can also write the value at time t equal to infinity here. So this is the first step. In the second step, we deactivate all the independent sources and find the transient response let us say this is xt by using the the Kirchhoff's laws. And there are two laws here. We will both be using the KCL as well as the KVL. In step 3, we will determine the roots and the response is evaluated. Whether or not the system has an underdamped response, overdamped response, or a critically damped response, it depends entirely on the roots which are calculated in step 3. In step 4, we make the total response of the circuit by adding the transient response xt of t plus the steady state response, which is the xSS of the t, which is this one. This is the xSS of t, and here the circuit comes into a steady state mode. So in order to have a better understanding, let's undergo an example here. So suppose that we have a voltage source. Here we have a switch which is operating at time t equal to 0, and here we have capacitor. This is a 12-volt source. This resistance is 4 ohm. This is 1 Henry. This is 2 ohm. And here we have this 0.5 farad. Across this capacitor we have this voltage V, and through this inductance we have the current I, and this switch is going to turn on at time t equal to 0, and it is required to find out the complete response of V and I for time t greater than 0. Now if we look onto this particular circuit, we are not sure that after time t equal to 0 whether or not this is a series RLC circuit or a parallel RLC circuit, and therefore we have to follow these 4 steps which are outlined above. So as a solution, we will go using the step number 1. The step number 1 is to find out the initial conditions and the steady state conditions. From this particular circuit, if this switch is open for a very long period of time, then I can redraw this circuit as inductor replaced by a shorted path. This path is open, and here this capacitor is replaced by an open circuit. So this is V0 negative, this is I0 negative, and this is the equivalent circuit. Here we have I0 negative is equal to 0, and that is equal to I0 positive, because we know that the inductor opposes sudden change in the current. We also have V0 negative equals to 12 volt, and that is equal to V0 positive. So here we have the initial conditions computed, and therefore we can proceed with this circuit with step number 2. However, it is wise to find out the steady state values at the end of a circuit as well. So at time t equal to infinity, we shall have this inductor shorted again and this capacitor open again, but we have this switch closed, and therefore at time t equal to infinity, the circuit will look like this circuit. Here we have, this is V0 at infinity, this is I infinity, this is 4, here we have 2, and this is 12. At time t equal to infinity, I infinity shall be equal to V over R. So this is 12 divided by 6, and this becomes equal to 2 ampere. And consequently, if we apply the voltage divider rule, the voltage across this 2 ohm resistance shall be the voltage at time t equal to infinity across this capacitor. So V infinity is equal to 2 cross 12 divided by 4 plus 2. That is equal to 24 divided by 6, and that is equal to 4 volt, right? So these are now, we have computed the initial conditions. We will now proceed to step number 2. Step number 2 is to deactivate the independent sources, and then we will find out the transient response by using the Kirchhoff's laws. So we will use the Kirchhoff's voltage law, the Kirchhoff's current law, to find out the transient response here. For this, I will redraw the circuit at, this is step number 2. At time t greater than 0, the circuit becomes so we have deactivated the source as given in this step 2. We have this plus 1 is V, this is 4, this is I. So now we will have to apply the Kirchhoff's laws on this circuit to find out the transient response. And for that, we will apply the KCL at this node A, and we will apply the KVL here in this loop. So applying the KCL at node A, we know that this current I is into this node A, so this is minus I, plus V over R is this current which is flowing through this 2 ohm resistance, and we have some current IC which is flowing here, and that is equal to 0. So this I becomes equal to V over 2 plus C is 1 by 2, so this is 1 by 2, this is dV by dt. This is my, let us say this is my equation number A. Now if I apply the KVL in the circuit, then I do know that I have current flowing into this terminal, so this is equal to 4I plus the voltage across the inductor is L di over dt plus this voltage V, that is equal to 0. So this can be written as 4I plus di over dt plus V, and that is equal to 0. And this is my equation number. This is my equation number B. Now the things are quite evident that we can substitute the value of I into this equation number B if we want to find out the voltage V for this given circuit. So substituting that becomes equal to 2V plus 2 dV by dt plus 1 by 2 dV by dt plus 1 by 2 d square V by dt square plus V, and that is equal to 0. Now this equation can be simplified in terms of the order of the derivative. So d square v over dt square plus 5 dv by dt plus 6v that is equal to 0. And now this can be transformed into the characteristic equation as s square plus 5s plus 6 that is equal to 0. This is the characteristic equation, and it can be found out by using the quadratic equation. And if I solve this particular equation, then I get two values of S1 equals to -2 and S2 equals to -3. Now this value S1 and S2, they are both the real values and they are distinct values, and therefore the response is overdamped, as I have explained in my lecture on the second order RLC circuit. So because this response is overdamped, I can write it as an overdamped response here. So based on this thing, the solution here for Vt is equal to V infinity, or VSS, they are one and the same thing, plus A1 e to the power S1t plus A2 e to the power S2t. This is a general equation for the overdamped response. To find out the values of A1 and A2, initial conditions are required. And let me write the general forms of the overdamped response here. For an overdamped response, the coefficient equations are such that we have x naught equals to xf final value plus A1 dash, plus A1 plus A2, and dx over dt that is equal to A1 S1 plus A2 S2. So based on these two equations, we can make this general solution into a particular solution. So we have, for the first one, we want to find out what is V0, that is equal to V final value or V infinity plus A1 plus A2. In the first step, we know that this V naught is equal to 12 volt, whereas the final value is equal to 4 volt. So this becomes equal to 12 is equal to 4 plus A1 plus A2, and this gives me this A1 plus A2 equals to 8. Now I will go for the second equation, which is this dx naught over dt. So this is dv naught over dt plus is equal to A1 S1 plus A2 S2. Now in here we have to find out what is this dv0 plus over dt, and this can be computed by circuit here, this circuit here, because if we know what is the value of the IC, we can find out what is the value of dv0 plus over dt. So to solve for this thing, I will again, let me redraw the circuit here. This is the circuit. This is 12, 4, 1, this is 2, and this is 1 by 2. Here we want to find out what is this IC. Here I have this I. So I0 plus is equal to IC0 plus V over R current through this 2 ohm resistance. So this I0 plus is equal to 0. So IC0 plus VC is 12 over 2. So this says that this IC0 plus is equal to minus 6 ampere. This is minus 6 ampere. And therefore, this dV0 plus over dt, which is equal to IC divided by C, becomes equal to minus 6 divided by 0.5, and that is equal to minus 12 volt per second. This minus 12 volt per second, I am going to substitute this in here to get the value of this A1 and A2. So this can be written as 12 equals to 2A1 plus 3A2. So we have the roots in the negative sign, so we cancel out the negative from this 12 and we come up with this equation. Now this equation can be used in connection with this equation. So if I solve these two together, then we have A1 equals to 12 and A2 becomes equal to minus 4, and consequently this equation, which is a general solution, will then become equal to a particular solution, because all the unknowns are now available, and this Vt is equal to 4 plus 12, and this 4 is, by the way, this is V infinity. We have already calculated it here, that is equal to 4 volt. So that is equal to 4 plus 12 e to the power minus 12 minus 2t minus 4 e to the power minus 3t volt, and this is for t greater than or equal to 0. So in order to check it, if it is valid for t greater than or equal to 0, we can simply put this t equal to 0, and once we put this t equal to 0, then we have this particular V naught equals to 12 volt, and this is the same thing as we have calculated it here. It should be 12 volt. At time t equal to infinity, the voltage should be equal to 4. So if I substitute this t equal to infinite, then these two terms become 0, and consequently this V infinity is equal to 4 volt, and therefore this equation is valid. Now to find out, if someone is interested in finding this current I, then this current I can be calculated as by using the KCL. So to find I, this is equal to Vt over R, which is equal to 2 plus C dV by dt, and by putting the value of these two things, that this I is equal to 2 plus 6 e to the power minus 2t minus 2 e to the power minus 3t. So what I have done, because I know what is the value of this Vt, I have divided it by 2. So this will be the current through the resistance of 2 ohm. To find out the current through this capacitor, this voltage is being put in here of this dV. So we get 0.5 into minus 2 into 12 e to the power minus 2t minus 4 into minus 3 e to the power minus 3t, and that gives me 2 minus 6 e to the power minus 2t plus 4 e to the power minus 3t, and this is the answer for the current. So the last thing that I would like to summarize here is that when we compute the roots, this is very important. When the roots are computed and we want to find out the response, then for an overdamped response, the S1 and S2 are straightforward, as I have explained in here in this example. For an underdamped response, S1 and S2 provides us information about the alpha and the damping frequency omega d. So these two values are used in the general expressions. For the critically damped response, the value of alpha comes from the root as given in here, and therefore you can solve all the three cases for any given circuit. If it is not possible to identify whether the circuit is connected in parallel or is it forming a series network. That's all for today. I hope that you understood what I have tried to explain. Till the next lecture, take care. Allah Hafiz.